Hey everybody, this is going to be lecture 15. This is my overview of the stuff that you need to do assignment 15. This is on the chain rule. The chain rule is kind of it seems like a funny name for folks in the US. In Britain, a lot of times people will talk about it chaining functions together, where we say composing functions. But that's what it's about, it's the figuring the derivative for compositions. So let's get started here. The chain rule, it's finding the derivative of a composition. Now remember, we picture a composition like this, and I think maybe you see why folks in other parts of the world might call that a chain. The input goes into F, and then F's output goes into G, and then finally what comes out, because the value that X is on this line, this input to F, but the value that's on the line between F and G, that's F of X. We've transformed X into F of X. And so G is receiving F of X as its input. And that means this is G of F of X that comes out. The composition really is what you get when you sort of think about taking that pair of things, one after the other, and calling it a single entity. Watch out for order here. You call this GOF, although, well, I guess the smart thing is to say read it right to left. That's G little circle F, which is the composition of G. Well, let's say it this way: F first, then G. All right, even though you read G first and then F if you're used to reading left to right. All right, so let's try to. I want to try to illustrate for you with a GeoGebra window why this thing works the way it does. So here's the GeoGebra window. I've started it out with a blue graph in there. I guess we don't need this. That properties for. This thing is, let's see, where is it? It's this function. G of X is X plus 2 squared over 4, more or less random, okay? And I also picked a point, not entirely randomly, although, you know, you should think of this as some random position. The reason I picked it where it is it's very convenient to have the X coordinate of the point be 0. But the Y coordinate is determined by the function involved. If the X coordinate is 0, let's see, we got 2 squared over 4, which is 1. So you see that's the point involved. I've also got on this page, or at least what's visible so far, is a slider for a variable k. Okay. So the first thing I'm going to do is just turn on a point here. It's labeled B. Why isn't it visible? Oh, because my slider value is at 1. Let's back it up. I'm not sure what's the best spot for that sucker. Anyway, the idea here is that we've got the function G, and the position of the slider, which is going to be determined by my fingers, is sort of that precomposing function. It's the F. Okay. Now, really, I guess in this instance, we probably should think about time as being the input, because I'm going to, based on the flow of time, adjust this slider position, and we're going to see different scenarios for how B moves as it passes through A. Maybe let's get that part done first. If I move B up, if I move this value K up in a kind of a smooth, uniform way, B passes right through there, and you know, that's, I guess, what you would more or less expect, right? But I could pass my point B through there in lots of different ways. I said we could move at a nice, smooth, slow pace, and then basically how fast B is moving in the up-down direction is determined by how slanted is this curve at that point. It's really the derivative of our G of X. That's what you get if you think about moving this guy at 1 unit per second or 1 unit per time unit. If the speed of this thing is 1, then the vertical speed is strictly determined by the ramp we're on. On the other hand, what if I go like twice as fast? Well, now I'm moving the same distance in less time, right? So I had to be moving faster in the vertical direction. What if I really give it a zip? Go zip. Then it passes through this location at a very high speed. And I'm thinking about this in the vertical direction. I hope that part's clear. I think it's useful to see that, to really see the precomposed functions. So I've made a couple of them here. The first one, h of x, is a cubic function. And I've put a point, let's turn off b, I've put a point here c, which is using h of k as the x-coordinate and g of h of k. That's truly the composition of g with this function h of x. Now, you don't really need to see what h of x is, but do notice some of its features. Its derivative right here, its tangent lines are darn near horizontal. In fact, I believe right at the origin they are horizontal. So its derivative is quite close to zero in this whole region. On the other hand, its derivative is quite high out here. Now, if we run the slider with c there being visible, actually now I'm going to hit the play button so that I don't have to try to hit it, at a smooth speed. I hit the play button. That slider is going to smoothly transition from -1 to +1, from its low limit at -1 to its upper limit at 1. And watch what happens to the point C. Were you expecting that? What happened there is, let's run it again. It starts out traveling at a pretty fast pace, and then as it approaches the value where x is 0, it slows down and stops, in fact. And then it takes off again. What's happening? Well, the x-coordinate of the moving point, which is the input to our blue function, that's being controlled by the red curve, and the red curve's derivative is 0. So it's like it's just like I took the slider and paused it halfway through. It's that. Let me show you a different pair of things. Turn those guys off. This is a function j of x, which has a rather different behavior. It's actually the cube root function. This guy also goes from -1, -1 to +1, +1, but it does it in a very different way. See how its tangent is near on vertical? In fact, it literally is vertical right at 0. And then it's lower out here. Now, how will the point that's controlled by j of k, this green function, and g compose with j of k? I'm basically precomposing different functions with our g of x. How will that behave as we play the slider animation? Starts out going really slow. It's not moving up very fast. Holy heck, whoa, it took off. Did you see that it went through that point at an enormous speed, vertically? I mean, side to side, it wasn't going that fast. It was in the vertical direction that it was going crazy. Let's look at it one more time. Slow right now, right? If you're just keeping track of its vertical position, its horizontal speed is always the same, because that's really determined by k. But it's no, I think I'm wrong about that. I'm totally wrong about that. Anyway, that's the vertical direction that we care about. That's the composition of the made-up function here, j first, followed by g second. All right. It's actually also kind of fun to see both of these points moving at the same time, because they both begin and end at the same points, but the way they behave is utterly different. One takes off out of the gate, and then when it gets halfway there, it stops and hangs out for a while. The other one races through that point, and then towards the end, I guess I need to zoom out just a little bit so we can see them both arriving at the same point together. And let's try it one last time. C takes the big lead, but then it dawdles around there. D goes past it at a high speed, and then C says, whoa, I better catch up. And they both come together at, well, the x-coordinate at that point is 1. I'm not sure what the y-coordinate is. It's whatever this function evaluates to when x is 1. All right, so that's all well and good, I suppose. The point of it was to get you convinced that when you have a composition like that, you're not just concerned with the slope of the function itself, but also the slope of the inner function. By the way, that's important terminology I should do. When you have GOF, if you write it in the form of the Euler notation, it's G on the outside and then f of x on the inside. So for that reason, we call G the outer function. Ooh, this pen is running out. Outer function, and then f would be the inner function. So here's what the chain rule actually says, since we've gone this far. You're taking the derivative of g of f of x, and that's a derivative with respect to x. Figure out how the composition's value changes when you change the x a little bit. And what you get is, well, I'm gonna lie to you slightly at first. What you get is what I told you in the last lesson is the error people do with the product rule. You just multiply g prime and f prime. That's slightly a lie because I've dropped the arguments. I haven't told you where these are evaluated. And so let's just say we need to evaluate them appropriately. So what do I mean by appropriately in this case? Look at the picture above. X is being fed into F, right? So at a particular X value, F's input is X, of course. But G's input is not. G's input has been changed by F into whatever F of X is. Well, those are the places we need to evaluate. F prime, that guy you evaluate right at X. But G prime, you don't want to find out what it is at X. You want to find out at the spot where its input corresponds to what happens when things are at X. In other words, that guy needs to be evaluated at f of x. Now this is a little bit ugly, so let's restate it nice and clean. The product rule is for the derivative of an outer function applied to an inner function, g of f of x, and let's just use the prime notation now. It really is g prime times f prime. But those functions are evaluated, well, f literally has x inside of it. So the argument to f prime is x. G's argument is f of x. And so that's what the argument for g prime is going to be. I think this is a case where the dropping arguments is probably not a good idea. Keep it straight. G prime of f of x times f prime of x. So we better do some examples of this. I have a couple in mind. One of them is, I'll write it first without identifying what the functions involved are, but we've got x cubed in parentheses, and then that's squared. Okay. So what are the functions involved? Well, cubing and squaring. Which happens first? This, just identify this as f, or g of f of x. What's the f of x and what's the g of x? This guy is the outer function, is the squaring, and the inner function is the cubing. So if I work this out, if I'm going to do that, that formula, I'm going to need to figure out g prime and f prime, aren't I? G prime's easy. Derivative of a squaring is doubling, 2x. And f prime, its derivative is 3x squared. Power rule, right? 3 comes out front, the exponent goes down by 1. So if we try to work out g prime of f of x times f prime, it's going to be g prime is doubling, so it'll be 2 times whatever. And f prime is 3x squared. I always do it that way, by the way, sort of leave a blank for the x in the g prime, and then go back in and fill it out. What am I supposed to be sticking in the parentheses there? F of x, which in this case is x cubed. And so taking everything together, you see you've got x squared and x cubed, total of x to the fifth, and a 2 and a 3. This is 6 times x to the fifth. Now, okay, that was a contrived example, and there's a whole other way to do it, which is nice to check, to verify that it does indeed work the other way. Can you actually do the algebra to square the cube of x? Sure. Power to another power, you just multiply the powers. So that's really equal to x to the 6th. So what's the derivative of x to the 6th? That's a simple power rule thing, and you get 6x to the 5th. Obviously, this was way quicker and easier than all of that rigmarole, but this was as I said, a simple example designed to give us confidence that this rule is really right. And trust me, there are times when you have no route such as this. You can't just do the algebra and then take your derivative. Like, what if these things weren't simple powers? Maybe they were exponentials or logs or something. All right, so that's a nice example. Here's one that's a little more exciting. What if we have the e to the x function with the x squared function inside of it? So what's the inside function? What's the outside function? Well, the g and the f. Ask yourself what happens to x first. The inner thing is what happens first, and PEMDAS, right? The power happens before the e to the whatever. So we're first squaring x, and then we're exponentiating. F of x is x squared. G of x is e to the x. What are the derivatives of those? Well, f prime is 2x, and g prime is unchanged. E to the x is that weird function that is its own derivative. So, how do I take the derivative of this guy? I take g prime and evaluate it at the place where it was evaluated before. That means nothing changes, right? The e to the x remains e to the x, but we don't stick x in, we stick x squared in. So you get e to the x squared times, well, we also have that term part of the chain rule that involves multiplying by the derivative of the inner function, so times 2x. Now, that shape should be something that becomes familiar to you. It turns out if you have e to the any function, f of x, and you want the derivative of that, you're going to get something that looks more or less like this. E to the f of x prime is going to be e to the f of x times f prime of x. So you can stick all kinds of different functions in there where f is, and it's very easy to work out the derivative in that situation. All right, we're going to end this with a little discussion about the quotient rule, because the quotient rule, I mean, if you recall how that looked, it seems like it comes out of left field. And so I'm going to show you where it actually does come from. We're going to derive the quotient rule by just being careful about using, well, the chain rule that we just learned and the product rule. So remember what this is about. You're taking the derivative of a fraction made out of two functions, f of x in the top and g of x in the bottom. The first thing I'm going to do is say, well, don't do division. Turn it into multiplying instead. So, and this is perfectly legal if you want to think about it this way. It doesn't really change anything to say this is f of x times 1 over g of x. It changes it in this sense, though. It changes our emphasis. Now I'm looking at the derivative of a product. Of course, if I'm going to do the derivative of a product, I'll need to be able to take the derivative of both parts. And here's where the chain rule comes in. See, that thing that I've just written is the derivative. Well, the f of x doesn't change, but the g of x could, yeah, sorry, that's at times. That g of x could be written as g of x raised to the minus 1 power. See, a negative 1 power is the same thing as putting 1 over that thing. And that looks like a composition. That looks like the g of x is the inner function and raising to the minus 1 power is the outer function. So do we remember how to take the derivative of something to the minus 1 power? If I have x to the minus 1, and I like the derivative of that, sure, the minus 1 will come, it's power rule, minus 1 comes out front, and then the exponent gets dropped by 1, and that becomes minus 2. So let's go ahead and use the product rule on these suckers, and we're going to need that part when we go to take the derivative of the g of x to the minus 1. All right, so it's going to be f prime of x times g of x. But, you know, g of x is this whole thing. It's actually this g of x to the minus 1 power. We'll just write it like that. Plus f of x. Remember, we have f prime, then g, and then we have f, then g prime. And right now, all I'm going to do is say we need to take the derivative of that thing, g of x to the minus 1. All right, so let's work with this. What I'm looking at there, f prime times g of x to the minus 1, that's really f prime over g. F prime of x over g of x. This other bit, remember how the derivative of raising to the minus 1 power played out. So we'll have that derivative, not evaluated at x, but evaluated at g of x. That's how this chain rule plays out. And then times the derivative of the inner function here, which was g of x. I still have some algebra to do. But one thing is, I hope you can now see where the minus sign in the quotient rule comes from. It comes from that negative 1 that came out of the power rule for taking the derivative of the negative first power. I think I'm going to need more paper, but let's go as far as we can on this sheet. F prime of x over g of x is what's in that first term. This guy is, well, the minus sign is, the subtraction comes from that minus sign. Notice we have, oh, sorry, I hope you guys didn't get fooled by this. This last bit is missing a prime. Right, that was the derivative of the outer function applied to the inner function and multiplied by the derivative of the inner function. Sorry about that. Yeah, so we've got minus f of x and g prime of x in the numerator. And that g of x to the minus 2, that's really a g of x squared down below. So we have g of x to the second power in the bottom of this right-hand half of the thing, and f of x times g prime of x. Almost there. If you've got two fractions and you want to combine them, you need to get them a common denominator. And in this case, what we've got in the denominator on one side is g of x, the other side is g of x squared. This side needs one more g of x. Right? Maybe I'll put this in a different color. We need to have a g of x in the top and a g of x in the bottom. Right? Really not changing the fraction by multiplying by the same thing in the top and bottom. Well, what does that get us to? Yeah, that gets us, well, okay. g of x squared is the common denominator, so that's down below. In the numerator, we'll have f prime times g in the first term. And then it'll be subtraction. And in the second term, it'll be f times g prime. So this is the quotient rule as we saw before. It looks just like the product rule in its form, where the f prime g, then f g prime, except it's got a minus sign, and we saw now where that came from. And I think now we see where the g of x squared in the bottom came from. All right, well, that's a great place to call it a day, I think. I hope you have a good rest of yours, and see you later.